oxygens. So we're going to place a 5 on the oxygens. Pull that out to 14 as well. Okay, so 5 oxygens. Let's put in our standard states. So liquid, gas, and gas, and gas again. So, oh wait, it says produce liquid water. All right, let's check if our equation's balanced. 4 carbons, good. 12 hydrogens, 12 hydrogens, good. 10, 4, 14 oxygens, 14 oxygens, we're good. This equation has now been thoroughly balanced. So now moving on to the next stuff. Standard heat of combustion of ethylene glycol is negative 1642.85 kilojoules per mole. Given that the delta H of formation of CO2, negative 393.5, and the formation of ethylene glycol is negative 500.7, what is the standard enthalpy of formation of water? That's the question here. All right. So what formula do we use? What? Yeah, so another way to say that is delta H reaction equals the sum, right, of the delta H formation of the products minus the sum of the delta H of the reactants. So we already have delta H of reaction, right? They gave it to you right here, negative 1642.85. So we're going to set that equal to delta H of reaction, negative 1642.85. And then as we said, that's the sum here of the products. So we're going to do 4 times carbon dioxide enthalpy, which is negative 393.5. And then plus 6. And then the water enthalpy formation is what we're looking for. I'm going to indicate that with an X. That's products here. And the reactants. What is the value for oxygen? They didn't give it to us. Why is it 0? It's in its elemental form, standard state, however you want to call it. So that's 0, so we can leave that alone. So the only reactant we really have here is ethylene glycol. So we'll do 2 times negative 500.7 because that's what it gives us. All right, now comes the long, treacherous task of doing the algebra for all this. So let's simplify this down. Let's multiply some stuff out. So we have negative 1642.85 equals 4 times negative 393.5. When you do that, you should get negative 1574. Then plus 6x. Then this is really 2 negatives here, multiplying by 2 negatives because you distribute the negative. So a negative times a negative, really a positive. So 507.
That is 6x plus 6x.
Yeah, okay, that's what that is. Plus 6x and times 2 gives us 1,000. Okay, plus 1,001.4. So we can simplify this down even further. So negative 1642.85 equals negative 1574 plus 1,001.4. And that'll give us here negative 572.6. Negative 572.6 plus 6x. Now all we have to do is solve for x. So add 572.6 to both sides. So negative 1642.5 plus 572.6 gives us negative 1,070.5, and it equals 6x. Divide both sides. 6 should get that the standard enthalpy of water is negative 1,070.25 divided by 6. Should get an answer of, if we're rounding here to 2 decimal places, negative 178.38 kilojoules So this question is just a bunch of algebra. But if you know how to do the algebra, then you're in pretty good shape. Any questions on this problem? All right, cool. Then move on to the next one.
How many of y'all got number 2? Pretty easy. Okay. Did this one require a lot of math?
I mean, you gotta put it all in calculators.
So,
As long as you get the formula right, then you're okay.
yeah, so how would we start this problem? It says 100 grams, 100-gram piece of osmium metal with the specific heat of 0.13 is heated to 500 degrees Celsius and is added to 200 grams of water at 25 degrees Celsius. That's the initial temperature of the water. Now, what is the final temperature of the water and osmium mixture? So how would we go about doing this problem?
Gotta get the formula for final temperature. Initial temperature, or sorry, for final temperature.
So, yeah, anyone, how would we go about this problem? So solve for delta T, okay, so. Which delta T? Because we have a delta T of the water and delta T of the metal.
You have the solution.
Was it? So we know that the metal is going to lose heat, right? And that is equal to the heat gained by the water, right? But we don't know the heats that, they didn't tell us anything about the heats. But what do we know that Q is equal to?
Who is equal?
Yeah, so negative MC delta T of the metal equal to the positive MC delta T of the water, right? This is all because Q is equal to MC, mass times the specific heat times the change in temperature of whatever it is. So now we also know that delta T is equal to final temperature minus initial temperature. And what can we say about the final temperature of both the water and osmium?
Reach equilibrium.
They're gonna be the same, right? Because eventually it comes to the point where all the osmium stops losing heat because all that heat goes into the water and they equilibrate, right? They come to a temperature somewhere in the middle. So we know T final is going to be the same for both of them. So therefore we can put this into both sides and we'll have to algebraically solve for T final, which is doable. But if you were here a while back, I would have showed you the equation that would have you could have just directly plugged all these things into and got your answer without having to do all the math. And does anyone remember that equation?
Isn't it mass times constant times temperature of the first element product?
Yeah, so
The mass times the constant time for the second over the mass times the constant plus the mass times constant.
yeah, so kind of a large equation, but broken down, it's really not too bad. So if we designate 1 as the metal and 2 as the water, then all you have to do is plug in all the information for each one into there, and it'll spit out the final answer of T final. All right. So you might say, oh, this equation has so many different variables. I'm not going to memorize this. I'd rather just do the math. But in reality, if you eliminate the T's, and then this is what I said, so you're probably going to hear me say, those of you that already heard me say this, if you eliminate the T's from the numerator, it's pretty much the same thing over the same thing, except the numerator has the temperatures, right? So it's not too difficult of an equation to remember. And this will help you bypass all the algebra that you need to get to this point. Because all this equation comes from is when you solve for T final using this equation here. Right? So now what we just have to do is plug in all the information, so. If we designate, let's designate the water as one, so all the variables with the one will be for the water, and then 2 will be for the metal. So the mass of the water was 200 grams. The specific heat of water is something that we have to know. And the initial temperature of the water was 25 degrees Celsius. And that's multiplied by the mass of the metal, specific heat of the metal, and the initial temperature of the metal was 500 degrees Celsius. And that's all divided by the mass of the water, again, so this is 1 times the specific heat of the water plus the mass of the metal is 100 times the specific heat of the metal. And what did y'all get if you put this into your calculator?
32 Celsius.
32 degrees Celsius. Is that what everyone else got? Okay. So T final. You should ask yourself, does this answer make sense? So when we look at osmium, osmium has a really low specific heat, which means that, and water has a very high specific heat. So it's going to take a lot of energy to heat up the water, whereas it's going to take not so much energy to bring down the metal, right? So we expect that the final temperature lies closer to the initial temperature of the water than to the initial temperature of the metal, even though it was at a 500 degrees Celsius. All right, so any questions on this one? Yeah. Yeah, so remember, negative, it means, the negative means that it's losing energy. It's losing heat. So the one that is hotter in temperature is going to lose the heat and go into the one that's colder, right? Like if you put a hot pan in cold water, the pan is going to transfer its heat to the water. So the pan's going to have a negative Q, whereas the water is going to have a positive Q. Yeah, so in this case, the osmium was really hot, 500 degrees Celsius. We put it in cool water. The metal was negative, it lost the heat, and that heat went and was gained by the water. No questions?
All right. Number 3, calculate the standard enthalpy of formation of liquid methanol using the following information. So we have all these reactions, right? And you probably have to do some like flipping and manipulation to them. What which law is that? We have to do all the flipping and manipulations of delta H. That's his law. So it says the standard enthalpy of formation of liquid methanol, right? What even is a formation reaction?
Oh, the pure elements that add up to the compound.
Yeah, in a way. How many moles of the product do we? Yeah, 1 mole of product. So yeah, what you said was like completely correct, but you just had to add that 1 mole of product there. But you got it in the end, so that's good. So it seems to me here that we're using carbon graphite. We're just gonna run with that. So carbon graphite, it's already in its standard state. We have a hydrogen in here, right? What's the standard state of hydrogen? H2 gas. H2 liquid, H2 solid, H2 gas. H2 plasma ether. All right. What about O2? Is gas. How many oxygens are there? What, I already said it, never mind. O2 gas. Then we're gonna form, right, CH3OH liquid. Only one of these. All right. If there's one of these, right? Let's balance out our equation. So there's a 2, we're gonna put a 2 in front of the hydrogen, right? Because that makes the hydrogens equal. Carbons are already balanced, 1 and 1 apiece. And then what coefficient do we put in front of the oxygen? Because there's 2 on the left and 1 on the right. I heard it somewhere. 1/2. Because again, remember, we need to form one mole of product. So 1/2 times 2 is 1. So dividing by 2, multiplying by 1/2, same idea, plan. All right. Now we have our goal equation, right? Now our goal here, our goal is to make the goal equation. Right off the bat, CH3OH, is it in our product side or reactant side? Products. And I see one equation here, the third one. CH3OH is on the reactant. So, as Keon said, flip it. So, CO2 plus 2H2O becomes CH3OH plus 3/2 O2. All right. If we flip it, what happens to the sign of the delta H? Turns the opposite sign. So this negative 726 becomes a positive 726.4. All right. Now we have our C graphite, right? We don't have one H2 in this equation. How many H2s do we have? Or H2s? 2. And then we have 1 in the top equation, right? So we got to multiply it by 2. This, so what I mean is the second equation has to get multiplied by 2. So we have here 2H2 plus 1/2 times 2, that's 1, O2. I'm being lazy here and not writing out the states, but you definitely should write out the physical states. 2H2O. All right. So we have most parts of our equation sorted. Now, if you notice, right, with our O2, we have one O2 on the top equation, so that's 1. Then we have another O2 here in our second equation, so that's 2 O2s total, right? And then we have 3/2 O2 on our product side. So when we add those together, what is that going to make?
2 plus 3. 5 over 2.
Remember, we don't add them because they're on different sides.
On the side, yes, we get 1/2.
Exactly, 1/2. So 2 and then 3/2 is 1.5. So that's 1/2. So that being said, we're all ready to make our goal equation. So C graphite, I'm just gonna write this out again. C graphite plus O2 makes CO2 gas. All right. We can cancel out some stuff, right? So CO2s, there's 1 on each side, so those go away. H2s, we don't do anything with those. H2Os, there's 2 on each side, those can go away. And then as we said with our O2s, the product side go away, and we're left with 1/2 O2 on our reactant side. All right, I didn't go over this till this point, but we multiplied the second equation by 2, right? What happens to the delta H?
Multiplied by 2.
Oh, to triple. Yeah. Yeah. Okay, so we double it. Not tripling, not dividing by 2. So 285.8 times 2. 285.8 times 2. We're gonna get negative 571.6. All right, now we have all the information, right? Our equation is equal to our goal equation. Now we can just go ahead, add up all these delta H's. So we're gonna do negative 393.5 plus a negative 571.6. So that's really minus 571.6. And then we're gonna add this to 726.4 since we changed the sign. If you do that, you get a final answer here with all the delta H's added of negative 238.7 kilojoules per mole.
Right, but don't you add the 2 negatives together?
What do you mean?
Don't you add them all together?
Yeah, that's what I just did.
2 negatives. Oh, I was thinking multiplication.
Yeah. All right. So your final answer, negative 238.7. Any questions there? Right.
All right. So, which gas has molecules with the smallest average molecular speed at 25 degrees Celsius? So the reason we give you a temperature here is because it's important to realize that temperature is proportional to something energy related. Do y'all know what that is? Yeah, so temperature is proportional to kinetic energy. And we know that kinetic energy is proportional to the mass and the velocity, right? So this is important idea for us to be able to solve this problem here. So if they're all at the same temperature, that means they all are going to have approximately the same kinetic energy, right? So the only difference between them is going to be the mass and the velocity, right? So let's look at, and if we're looking for the one with the smallest average molecular speed, that means that we're looking for the one with the smallest velocity. But in order to make this ratio true, so that way T is proportional to kinetic energy, that means the mass has to increase, right? Because if one goes down, that means the other has to go up. So in order to make that cancel out when it decreases, that means the mass has to go up. So what we're really looking for is the one that has the smallest or the largest mass, which is going to tell us the one with the smallest molecular speed.
No matter high temperature.
What? All right, so out of all of these, which one's going to have which one has the highest mass? Krypton. Yeah, so it's really just that easy. And if you don't even want to think about it in this sense, you can just think, all right, if we're all at the same temperature, what's going to move faster? Something that's lighter or something that's heavier, right? So the one that's going to move faster is something that's lighter, right? Therefore, the one that has the smallest average speed is going to be the heavier one. So that's just a more simplified way of thinking about it. It's really, you can think about it either way, it doesn't matter, right? As long as you get the right answer, I guess. So are there any questions on this idea here? Okay. Are y'all sure? Everyone got this? All right, sounds good. All right, Rich.
Alright. Number 5, I'm gonna say is the hardest one on here. Solely for the reason of, I don't remember us ever going over it.
Did it once.
Yeah.
And Professor Arnold.
Point.
We didn't go. over it.
Yeah.
I figured you-
Also, point being that, yeah, we didn't go over it too much, so. All right, so which of the following reactions would have the greatest difference between delta H, delta E? So let's go through all our conditions, right? When does our delta H equal the delta E? Like they're the exact same value.
When they create a standard formation. For the standard entalpy formation.
Not really. It has to do with a certain physical state.
Oh, maybe. Oh, let's.
Right? Anyone else have an idea? Here we go. So, well, which one is it though? When the moles of the gases are equal, or when there's no moles of gas? And then.
Yeah.
Hope. All right. From my understanding, right? The delta H equals the delta E when the moles of gas are the same. Like 100%, like the moles of gas are equal on both sides. That's when the delta H equals delta E. Then there are other conditions where delta H is approximately delta E. So they're like around the same. And which ones would those be? Yeah, no gas, that's one. And second, no gas. And what's the second one? I mean, there's really one more scenario we haven't gone over, right? There could be no gas, the gas could be equal, or yeah, exactly. So the moles of gas are not equal on both sides. So for the sake of this exam, and believe me, we verified this morning, you do not need to worry about whether like the delta H is like greater than the delta E or anything like that. He doesn't care about greater or less than, he just cares about like if it's approximate. So it's like around the same ballpark. Because the whole idea is the value will increase or decrease, but not really by much. So the mole of gas are not equal on both sides. So now that brings us to this question. Where will the delta H and delta E have the greatest difference? What is or let's go through it step by step. As Dylan says, we gotta put you all in the trenches first and then pull you all out. Where will there be the greatest, or where will there be a difference at all, really?
What is the greatest difference?
Yeah, exactly. Whichever has the greatest difference in moles of gas. Whoever has greatest difference in moles of gas. So really the moral of the story here is the difference in moles of gas is how different your delta H is to delta E. So if you have less moles of gas, right, if your moles of gas are decreasing, then your delta H will be, like there's a lesser difference between delta H and vice versa, if there's greater moles of gas. So that's what we're looking for here, in a nutshell. We're looking for the change in moles of gas. So we have to increase greatest amount of moles of gas from our reactants to our products. So if we do that, there's for A, there's 0 moles of reactants, or 0 moles of gas here. There's 1 mole of gas here. So that's 1. We'll leave that to the side. There's 6 here, and then 7 here. So that's a -1. We went down by 1. Let's look at for C. Y'all probably would have guessed that with the coefficients, but let's go through it. So 18, right, on the products, and 15 on the reactants. So we increased really 3 moles of gas. This isn't a negative, it's a positive. +1, -1, yeah. Yeah, it's because work, right, is equal to -P delta V.
Can we cross out the ones that have like solids and liquids?
Why can we do that? Why can we? Can.
Oh, because they're like gases.
Or I should say, like, what about our solids and liquids? The volume is negligible, right? Like we can for the most part ignore the volume they have. It's going to be constant throughout. Gases, right? They change shape, change volume, all that. So this one has no moles of gas in it. We can deal with that. So zero really. And here, again, there's a 0 difference because 2 on the right, 2 on the left, 0. And here, there's 3 moles of gas. Here, there's 2 moles of gas. So again, +1. And as we stated before, right? So as we stated before, we're looking for the one with the greatest difference in moles of gas. As the gentleman over here said in the front, like 5 minutes ago, the answer was B. All right. What if they said least difference between delta H and delta E?
Either D and
Yeah, D or E, yeah, it would be E. Yeah, because E technically has 0. Or wait, sorry. It would be B. Because B, you actually go down. Yes. And then, yeah, there's other ones. So when delta H is approximately delta E, that would be D and E, right? Because the moles of gas either doesn't change or there is no gas. Yeah, bottom line, you're probably gonna have a question on it. Any questions on that? Right.
Number 6 is an interesting question, right? If y'all were here on Wednesday, which 1, 2, I think only 2 of y'all were here on Wednesday, might know how to solve this problem. Or maybe if you just thought outside the box. So if you were here on Wednesday, don't answer. But how did everyone else go about solving this problem? Who didn't solve this problem? Raise of hands. Okay. Who was able to? Yeah. How did you do it, Megan? Who did this to Megan? Not as good as I could if you had a microphone.
There's one thing called projection.
Oh my god. I'm bad at that. Okay, well, can you hear me now or
Yeah, that's
no?
good. That's good.
Okay, so I thought about the ideal gas law, which is PV equals nRT, and then I know that molarity is moles over volumes, and so I just solved for N over V, which is moles over volume, which is molarity. And then in the equation, you're given the pressure and the temperature, you know what R is already, and so you can solve for molarity by that.
Exactly, yeah. So she said, well, what is molarity? Molarity is, like Megan said, moles divided by volume, right? So in the ideal gas equation, there is moles and volume. So we can solve for moles over volume by isolating for moles over volume, right? That's exactly what Megan did.
And Celsius and the Kelvin.
That's another thing, yeah. So when you use the ideal gas equation, you utilize R, the ideal gas constant, and R is in specific units that require specific units of other variables. So for example, pressure needs to be in atmospheres, temperature needs to be in Kelvin, and volume will always have to be in liters. And yeah, moles is in moles, not millimoles or micromoles. So in order to get to Kelvin, we just add 273 to this number. 73. That would be 4, 9. So that's 594 Kelvin. That's the temperature. So now we just plug all this in. So it was 18 atmospheres over 0.0821 multiplied by the 594 Kelvin. And what did we get as our molarity, which was our moles over volume? What do we get as this? What is the number? What's the molarity of the gas? What? 137. 0.37. So 0.37, and it's going to be in units of what? We're solving for molarity, it's going to be in units of molar, right? Or moles per liter, right? So again, or it could have been moles over liters. So it's really not too bad of a question, right? It's just you have to think outside the box. You have to ask yourself, well, what is molarity? And then hopefully from there, you are guided to look at other equations that involve gases that utilizes gases and involves the variables that the molarity equation has, right? So it's not too bad. Any questions on that? No questions, all right. No questions, we'll do the next one.
All right. Coffee cup calorimeter, 11 grams of KMNO4 mixed with 75 grams of water, initial temperature 25 degrees Celsius after dissolution of the salt. Final temperature of the calorimeter contents 21.97 degrees Celsius. Assuming that the solution has a heat capacity of 4.184 joules per, you can write it like that, but joules per gram times degrees Celsius. And assuming no heat loss to the calorimeter, calculate the enthalpy change of the dissolution, KMNO4 units of kilojoules per mole. All right, what's the real thing that we're solving for here?
The solution or the heat capacity for. Enthalpy change.
Or what's that also like, or what's another word, or what's the symbol for that?
Delta H.
Delta H, yeah. That's really what we're solving for here, delta H. So in this Q paper of a question, it's important to look at what you really need at the end of the day. What I like to do is I like to underline like stuff I need. So 11 grams of KMNO4, 75 grams of water, initial temperature, final temperature 21.97, heat capacity. Yeah. All right, what's our main thing that we got to pay attention to in coffee cup calorimetry?
The reaction. Vice versa.
Vice versa, yeah. So Q of water equals negative Q of reaction. So what we really need to solve for, right, is Q of reaction. And we can do that using the Q of water. So the Q of the water, another way to write that is mass of the water times the specific heat of water, CH2O, then times the delta T of H2O. And if you look in our problem, we're given all of the information to solve for all of those things. So the mass of the water is 75 grams, specific heat 4.184, and the delta T, we have a final temperature 21.97, and the initial temperature of the water here is 25. So 21.97 minus 25. So 75 times 4.184 times 21.97 minus 25. Get negative 950.814. What are the units? Joules, not kilojoules. Remember, the specific heat is in joules, so or your final answer will be joules. So this is in joules. And it turns out that what Keon said was actually right in this case. So because
What do you mean actually?
I mean, okay. Nothing like that, but you know, it's what's it called? I was gonna say,
Well, just carry on. Fine.
all right. Yeah, you probably roast me later, but still. All right. So it's not actually right. Keon's a great student, smart. But yeah, negative 950.814 joules. Right. So this is the Q of the water. Yeah.
Don't add the.
Not yet. So because the reason being, right, in order to do that, we need the specific heat of KMNO4, which they didn't give to us in the problem. So there's no way we can do that. Instead, we find the Q of the water and then just flip the sign for Q of the reaction. That's the easier way to do it. Or in this case, the only way we can do it because we don't have the specific heat. But negative 950.814 joules. So what this really means, right, is the heat lost by the water is the heat gained by the reaction. So the reaction is going to be endothermic, right?
I changed the kilojoules though.
Yeah, we will change that to kilojoules. We could do that now. I usually do it later, but we can do it now, it doesn't matter. So 1,000 joules on 1 kilojoule. So we get negative 0.951 around here. So this is Q of water, right? The Q of the reaction would have an opposite sign. So this would be positive 0.951 kilojoules. All right. Delta H is equal to what? Yeah, exactly. Q the reaction over moles. So delta H was Q reaction over N. So we already have our Q reaction set out. Now we're gonna use the moles and stuff of KMnO4. So 11 grams of KMnO4. What I'm doing here is converting to moles. We do that by dividing by the molar mass. If we do that, we'll get an approximate molar mass of 55 plus 39 plus 64, whatever that is. 55 plus 39 plus 4, 8, 5. All right, approximate molar mass of 158. If you want to use all the decimals, you can. But for the sake of time, I've always rounded my molar mass to the nearest whole number. And it's worked for me. So 11 divided by 158. If you solve this out, you will get 0.069620, whatever, repeating. So I just round up to 0.0696. I like to keep my stuff in 2 to 3 sig figs. So we have our kilojoules, have our moles, all left is to divide them. So move over here, 0.951 over 0.0696. 1 over 0.066. Oh, sorry, this is 0.951 over 0.0696. Gives us a delta H of 13.66 kilojoules. Any questions there? Yeah.
So, I've been a similar question in lab lecture, or not lab lecture, or in the normal class. And that's the way I did it. Then Bradley Dustin said that you had to add the 4.184. Like the KMnO4, like you would basically add that to the 75 grams of water. Has to use around 4.1. Plus, it also says the solution, like the total water and KMnO4.
Oh, yeah, that'll do it. That'll do it, yeah. When it says the solution, you have to add both of them. That's where that comes from. So 75 plus 11, the way this goes is that's actually 86. So yeah, 86, and that specific heat times that delta T. So yeah, it's important to read the question so you don't do what I just did.
Solution equals Q of your reaction.
Yeah, you still do the same thing.
It's the same process except you're adding the.
Exactly. Nothing else changes other than the fact that you use the solution instead of the thing.
What do you add the word?
When it says solution, basically.
Q of solutions and the reaction.
Yep. Q of solution to Q of reaction. So yeah, it's not Q of the water, it's Q of the solution. Which really is the same thing, but.
Together, yeah.
So this should be 1090.27. Same process converted to kilojoules. Thousand 90.27. Then this would actually be 1.090. Then you're gonna do the same process, you're gonna get the same moles. So 1.090
You get negative 190.7.
That was from the fact that. Wait, 190 was, that was because this, I made the grave mistake of. Not adding in the solution. So this isn't Q of water, it's Q of solution. I was going to read your question. So what I did was this. Here's a bucket, right? Here's water. I was assuming there was only water in here. But the thing is, there's water and there's KMNO4. This KMNO4 is soluble. So you have to add in the grams of the water plus the grams of KMNO4, because that's the grams of solution. So you do that, 1.090 over 0.0696.
I still don't understand how I got negative 190.
Oh, it's because I multiplied all of these together.
Mass of the water times the.
Or no, not the mass of the water, mass of the solution. So that's the 75 plus the 11. So that's 86 grams total instead of
So
75.
it's 86 times 4.184 times negative 3.03.
Yeah,
Oh, okay, then everything else is just.
everything else is just the same, yeah. So instead of what I got, the answer is actually exactly 2 kilojoules higher. So 15.66, we should have gotten after that. All right, to re-clarify, because I didn't read the question, like my own advice stated. So to re-clarify, when it says solution, right, you add in both the water and the KMNO4. This comes from the fact that KMNO4 is soluble, so you have to take that into account. So 75 plus 11 gives you an 86 gram mass total. And the specific heat and delta T is the exact same. So 4.184, and then delta T is the same as it was. So you get negative 1090.27. Then from there, you do the same stuff. So Q of solution this time, or negative Q solution equals Q of the reaction. So you solve that out, divide by the same amount of moles, it should get out. You should get a delta H of 15.66. Yeah,
You only add the weights if it says the solution of the heat capacity, right?
yeah,
That one line.
yeah, when it says solution. Or if you know like something's soluble right off the bat. Cause it's like, you know, that's like the water plus that. Yeah, it's important to read the question. That's how it gets most people, including myself. All right, I know that was kind of a haphazard explanation. Do y'all have any questions on that? No? All right. Final problem. All right, number 8. So 0.5632 grams of benzoic acid burned in a calorimeter containing 1064 grams of water. Temperature rise of 8.54 degrees Celsius was observed. What is the heat capacity of the bomb calorimeter excluding the water? All right, so since it says it's excluding the water, there's no business of adding the masses together. The heat of combustion of benzoic acid makes negative 26.63 kilojoules per milligram. That's right. You can have units of kilojoules per milligram. So different that way. All right. So what's our equation again for bomb calorimetry?
L equals.
All right, you're close. C cal equals Q cal. What else is there? Yeah, that's one way to do it. So Q cal equals C cal times delta T. So really what we're doing here is we're solving for C cal. So that will equal, right, C cal equals Q cal over delta T. But you have to go a little backwards here. Since this heat of combustion stuff, that'll give us ultimately, when we multiply by moles and all that stuff, that'll give us Q of the reaction. So we need to flip the sign, get it into Q of calorimeter, and then divide by the delta T. So here, we're gonna start off with the heat of a combustion here. Negative 26.63 kilojoules per milligram. Then our task here is to convert this into kilojoules per mole, regular units for delta H. So to do that, 1,000 milligrams per a gram. And molar mass of benzoic acid is what value? Definitely not 40. The formula here is C7. Let's do it this way. C6H5COOH. Usually they give it to you, but I try to make this problem a little harder. Yeah. Not really, because y'all didn't go over naming of hydrocarbons, so. Yeah. Well, I mean, back when Dylan and I took the class, we went over naming of hydrocarbons, so we had to know like pentane and stuff like that. Yeah. Point being, y'all don't have to worry about that. So 12 times 7, that's 84, plus 6, 90, plus 32, 112. So 112 grams are in 1 mole. But this is really kilojoules times. We got to get it to kilojoules over moles. So there's a way we can do this. Might be a little unconventional, but you know me, I live for the unconventional. So negative 26.63 times 1,000 divided by 112 gives us negative 237.77. But if we cancel out our units here, oh, sorry, this should be milligrams. So milligrams cancel. And okay, 1,000 milligrams in a gram. Oh, that's where I made a mistake. Okay, I put grams up here. So really, our units do work out. 112 grams in 1 mole. So yeah, this isn't the answer. Negative 26.63 times 1,000. Then this is times 112. And if you do that, your units here should work out. Because you do get negative 298,000 or 2,982,560. And this is in kilojoules per mole. All I did here was really convert the kilojoules per milligram to kilojoules per mole. So 1,000 milligrams in a gram, and then multiply by the molar mass. So do that. We multiply by the moles of benzoic acid. So 0.5362. Then there are 112 grams here for every 1 mole. So we get 4.7875 times 10 to the minus 3. So doing the math here, we're gonna do 2,982,560 divided by 4.7875.
Did you get 1,982,560?
So that's when converting the kilojoules per milligram into kilojoules or kilojoules per mole.
What?
Hmm?
What?
For the delta H. Not the delta H, sorry. Yeah, for the delta H. Because you see how the units are in kilojoules per milligram? And that's not the proper units. So I had to go from kilojoules per milligram into kilojoules per mole. Or are you confused?
I don't know how you got that done. Because you're saying that equation equals negative 92,560.
Yeah.
But oh,
Yeah. So Then here, we're gonna do 2,982,560 divided by 4.785 times 10 to the minus 3. And so you should get, if we put this in scientific notation, 6.23 times 10 to the 10 to the 8th. 23 times 10 to the 8th. So this is the amount of kilojoules. So in other words, or this is a negative value. So this will be a negative value. So this is our Q of reaction. Yeah. Well, that's the moles of benzoic acid, yeah. Because we have grams here, and then this is grams per mole. So this is 4.7875 times 10 to the minus 3. Because we have a small amount of grams, even smaller amount of, we're dividing by a really large number, so that's a really small amount of moles.
Oh, the scientific notation, I was thinking.
Yeah, the calculator spit it out to me in scientific notation, so that's just what I ran with. So this is Q of the reaction, right? How do we get from Q of the reaction to Q of the calorimeter? With the sign. So 6.23 times 10 to the 8th kilojoules. This is our Q of the calorimeter. And all we're gonna do here, since we're solving for C-cal, is divide by the delta T, 8.54. But is this what we should be doing? Yeah. Oh, really? Like 12 times 7, 84. Oh. I mean, I don't know how much that'll change the answer, probably be minor, but 5632 over, we'll try it again, 112. All right, so the moles should actually be, oh shit, that's actually big. All right, the moles should actually be 0.005. So important thing, write down your things properly. So 0.005, and this part 2,982,560 divided by 0.005. Yeah, sometimes my brain thinks faster than my head, so yeah.
We get 0.005.
Well, that's a new amount of moles because what I did was I messed up. So instead of 5632, I put 5362. I messed up my moles.
So why is dividing it? That's not.
Kilojoules per mole. Oh shit. Okay, yeah. Point being, my head thinks faster than my brain. So, or I think faster than my brain. All right, but my case in point right here. So, yeah, I think faster than I can write. What I'm trying to say. So, negative 2,982,560 times 0.005. Now this is the right amount of kilojoules. Damn. Okay, 14,912.8. It goes to show you can still have a dumpster fire during the test, and as long as you catch your mistakes, you'll be fine. So this is now our kilojoules, right? So this huge number actually becomes 14.912.8. But heat capacity, right, normally is in joules per degree Celsius. We'll convert this to joules. 1 kilojoule is 1,000. So this is 14,900. There we go again. Okay, 14,913. This value. So we get 14,913 divided by 8.54, 414,913. divided by 8.54. Gives me a final C-cal of 1746.25. Yeah, 1746.25 joules per. Right. And you just use negative Q solid equals Q water plus Q cal. Solve for C cal from Q cal. Thing is, Cash, there's a problem with that because it says the heat capacity excluding the water. But really, the water is zero, so you'd be doing all that work for no reason. All right, so this is how you do that. And if your head thinks faster than you can write, slow it down. An hour and a half exam, and don't do what I just did. It's actually a good thing because I tell you what not to do, so that you don't do it.
But basically, don't feel like.
Exactly. That's 14,913 joules. Are we talking about this one? This one that I marked right here? Oh, no. This is in kilojoules.
Yeah, but you guys still have this there. Whenever,
I didn't.
by the mold.
2, 9, 2. This is not my day today. Yeah, that doesn't go with those. So yeah, this value should be 14,912. So 14,912.8 divided by 8.54 gives me this. Well, okay, I got the same answer, so it didn't really matter. Oh wait, no, it didn't. That's times 1,000. So this answer should really be times 1,000.
If you're hurting yourself, calm down.
912.8. So should get 149,128.12300. So what this actually should be 14,912.800 divided by 8.54. Now, yeah, the answer you get should be 1,000 more than what I got. So 1,746,229.51. The heat capacity is 1,000,000 joules. Probably not realistic, but there you go.
Take a picture of this.
I'm curious as why rather than milligrams.
Yeah, you probably could do it that way. It's probably a shortcut.
Yeah, that's what I did and I got right.
Yeah. So pay attention to your units, I guess. There's multiple ways to do these problems. So yeah,
Proud of you, Rich, for learning from your mistakes.
yeah. That's the best part.
Any mistakes.
Yeah. Thanks.
That was Rich, well, thanks for that.
Yeah, no problem. It goes to show I'm not God. I'm human like all of y'all.
Yeah, I'm only human.
All right, any questions over this stuff? Yeah.
Oh, why is it not negative? After you multiply it by the mole?
Oh, it's because we're solving for, that's Q of the reaction right on the right.
Oh.
So we flip it, so it's Q of the counter. Are you lucky shirt or something? Is that your lucky shirt? You've worn this like 3 times in a row. No one wants to strike the blue feet flowing through
No,
it.
I need them, bro. I need them for the 67.
This guy about to go into gear second on the exam. All right, get out of here. It's already like an hour or like half an hour over time. So yeah. Yeah, you do, but I flipped this equation, so you have to change the sign. Yeah, and then you add that up.
I had a quick question on the, I think it was number 3 or 4, the one with like the 4 equations,
Yeah.
4 formulas. What was the formula used to combine them all to get like that negative number?
That was the formation of methanol. So if we go back,
Is that products plus reactants?
you're talking about this one, right?
Yeah, 3.
Yeah, so that's called a formation reaction. So you form 1 mole of products. And then the elements all have to be in their standard states. So I kind of derived that equation from that.
Okay, and then, so then you do, like after multiplying and then everything would be. Would be 726.4 plus negative 751.6.
All this
Negative 393.5.
like right now, what is?
So that's a 571, yeah.
Oh, 571, yeah.
Water and solid.
So you flip it, manipulate it, those 3 equations
Uh-huh,
in a way to make that top.
alright, yeah,
That's basically all you gotta do.
alright, thank you.
I just change the notation accordingly, yeah.
Water, negative.
The final answer asks for what's the Q release, but our answer is negative 2. But the Q release is 200 or is negative 2?
The reaction